Okay, welcome back to our continued discussion on bonding. So we started out by talking about covalent bonding, both nonpolar and polar covalent bonding, and we talked about how those are differentiated from ionic bonding. Today we're going to continue that discussion by talking about ionic bonding and metallic bonding, and just a little bit about what we call network covalent solids. So let's go ahead and jump in to our PowerPoint for the day. Okay, so just a quick review. We remember that there are three basic types of chemical bonds. Those are ionic bonds, which result from the electrostatic attraction between ions, covalent bonds that result from the electrostatic attraction of protons of one molecule for the electrons of another that result in the sharing of electrons. And we have metallic bonds, where we have several metal atoms bonded to several other metal atoms. And so we're going to talk in more detail today about both ionic and metallic bonds. So just a quick reminder that the way we can quickly determine the principal character of the bond is to look at the differences in electronegativity. And so if the difference in electronegativity is greater than 1.7. So this is the difference between the electronegativity of the one atom involved in the bond and the other. Then that is going to be an ionic bond. If it's less than 1.7, it's going to be considered a covalent bond. If it's between 0.3 and 0.7, we would consider that a polar covalent bond. If it's less than 0.3, we consider that a non-polar covalent bond. Please remember this is just a general rule. There are lots of exceptions to this rule, but it gives us a starting place. Please also remember that this is a spectrum. Most covalent bonds have some ionic character, and many ionic bonds have some covalent character. So it is a spectrum, it's a continuum. So when we talk about bond character, when we talk about an ionic bond, this is a bond that is principally ionic in character. That means it is mostly like an ionic bond. And when we talk about a covalent bond, we're talking about one that is principally covalent in character. So what happens in ionic bonding? Well, the first step is that electrons are transferred. And this happens because there's a large electronegativity difference between the two atoms, and that is so significant that the pull exerted by the nucleus of one atom overcomes the pull exerted by the nucleus of the other atom, and the electron is completely transferred. So this generally happens if those electronegativity differences are greater than 1.7, because that means that one nucleus is much more effective at pulling electrons than the other is. When this happens, this is always exothermic. If it's not exothermic, it won't happen. That bond will not form. Okay, so the formation of bonds, whether they are ionic or covalent, is always exothermic. We know that there are two steps to this. The first one is the removal of an electron. That's ionization. When we talk about ionization energy, we know that that requires energy to remove that electron. We also know that there's electron affinity, which is when the electron is added to the atom that becomes an anion, and that releases energy. So we'll come back to that concept. Okay, so I said that the 1.7 is just a guideline. Electronegativity difference is not the final determination of ionic character. The best way to determine for certain whether or not something is ionic is to melt that compound. If it conducts electricity when it is melted, it is an ionic compound, because those charged ions are free to move around in the liquid, thereby conducting electricity. Dissolving in water is not a final determination, because there are many covalent compounds that do have at least partial dissociation. But if it is liquid, that is a final, and it conducts electricity, then we can be sure that it is an ionic compound. Okay, so we're going to talk a little bit about the energetics of ionic bonding. So if we're going to take a specific example, and that's sodium chloride. if we look at the first ionization energy of sodium, it's 495 kilojoules per mole. It requires 495 kilojoules to remove the electrons from 1 mole of sodium, just the first electron. When that chlorine atom receives an electron and becomes a chloride ion, it releases 349 kilojoules per mole. But this is 495 to remove, releases 349. That means that overall, we're still putting energy in. But if you look at this reaction, this formation between chlorine and sodium, this is an explosive reaction. So why is the formation of sodium chloride so exothermic? Well, there's more going on than just the removal of the electron and the addition of the electron. Here's our third piece. We have the energy to remove the electron. We have the energy lost when gaining an electron, but we also have an attraction. And that attraction is between the newly formed cation and the newly formed anion. And guess what governs the energy of that reaction? Coulombs Law. Okay, so Coulombs Law, we talked about when we talked about the context of the electron's attraction to the nucleus. Coulombs Law says the energy of interaction between a pair of ions is proportional to the product of their charges divided by the distance between their centers. Now notice, this time we're talking about energy, we're not talking about force, because when we're talking about energetics of ionic bonding, we want to make sure that we're talking about energy and not force. So this is why it's over R instead of over R squared. So we've put the constant in. We can also write this that energy is proportional to the square of the charges divided by the radius. This is the third piece. The energy that's released by this attraction is more than enough to make up for that 150 kilojoule difference. Okay, so this is the third piece. This is what makes all of these bond formations exothermic. Okay. Let's look at it from the other side. So now this is our sodium chloride crystal lattice. You'll notice that we have alternating positive and negative charges. Hopefully you remember that the green balls must represent the chloride ions, because we know the chloride ions are larger because they are anions, and the little purple circles must represent the sodium ions, which are smaller because they are cations. We know that ionic compounds form crystalline structures. They organize into this alternating positive and negative ions in what we call a characteristic crystal lattice. When I talk about salts in chemistry class, salt is another term for an ionic compound. All salts are ionic compounds, all salts form crystals. The stronger the attraction between the anions and the cations, the harder this lattice is to separate. And so generally speaking then, the higher the lattice energy, the higher the melting point. And that lattice energy is governed by Coulombs Law. So the bigger the particles are, if we go back to Coulombs Law, the bigger the particles are, the smaller this energy is going to be. Okay, if we have big ions, they're going to be farther apart. That R is going to be a bigger value. But the smaller they are, the higher this energy is going to be. Conversely, the larger the charges, the higher the energy. So what does that mean from a practical standpoint? It means that more highly charged ions are going to have stronger attractive energies. It means that larger ions are going to have smaller attraction energies or lattice energies. Okay, so let's take a look at what these look like. Okay, you guys are never going to have to draw these, but it's important to recognize that when we talk about an ion or an ionic compound, that they're always going to be represented by empirical formulas, because ionic solids don't form discrete molecular structures. When we talk about lithium niobate, we're not talking about one ion of lithium and one ion of niobate. We're talking about an entire crystal lattice structure where we have alternating positive and negative ions. This has a lot to do with the characteristics of ionic compounds. Okay, we have just said that if this crystal lattice has high energy, which this one would, then it's going to be very difficult to separate. Well, because they don't form discrete molecular structures, in order to melt salts, you actually have to break at least some of these ion attractions. And so the higher the lattice energy or the Coulombs attractive force, then the higher the melting point is going to be. So if we look at a particulate diagram of an ionic solid, we should always see alternating positive and negative charges. We may see larger and smaller positive and negative charges, and this arrangement might be slightly different, but whenever we see a diagram of an ionic solid, we want to make sure that we are looking for it to be alternating positive and negative charges, which leads us into another characteristic of ionic solids, which is that they're very brittle. Even though they're hard, they're brittle. And why are they brittle? Because if you have an impact on this crystal lattice and it dislodges the layers of the lattice, then instead of being lined up opposite charges next to one another, it's going to be lined up so that the same charges are next to one another. And that is going to cause repulsion, which is going to make the solid break apart. Okay, so let's jump ahead and talk about some metallic solids, and then we'll come back and do some practice problems. Metals are totally unique in the way that they bond. So in covalent compounds, electrons are shared in pairs in order to achieve that octet. In ionic compounds, electrons are pulled away or taken and given in order to achieve the octet. Metals, on the other hand, have empty d orbitals. They have lots of space in which their electrons can spread out. And so they have a very unique form of bonding. Instead of sharing electrons between two atoms or giving and taking electrons, they share all the electrons across all the atoms in the solid. So we call this the delocalized model, or we sometimes call this the sea of electrons. So those vacant p and d orbitals in the metal's outer energy levels overlap. Those outer electrons can move freely throughout the metal. Those electrons don't belong to any one atom. Unlike the covalent ones, they're not being held in between just two atoms. They are totally free to move around. This is why metals conduct electricity, because those electrons are free to move. It's also why they're so malleable and why they are able to be rolled into sheets and pulled into wires. So let's talk a little bit more about metals. So we can think of all of these nuclei as little round hard spheres. And so when we pack these all together, we call this the closest packing model. This means that every atom has 12 neighbors, one above, one below, 4 to each side, and then 4 more on the diagonal, or 6 more on the diagonal. So closest packing. But if you look at the image, you can still see that there are little spaces in between, and that's going to become very, very important. So this is what it looks like if we're just looking at a single layer. And again, you can see those little spaces in between. So when we talk about metals, one of the things that we talk about is something called an alloy. And an alloy is a mixture. It's not a compound. It is a mixture containing, depending on the type of alloy, frequently multiple metals. Okay, so in a substitutional alloy, this means that some metal atoms are going to be replaced by other metal atoms with similar size. So copper and zinc have very similar sizes. So if you have a compound, if you have a sheet of copper and you heat it up and you add zinc to it, the zinc will actually move through that sheet of copper and you will get something called brass. And brass is a substitutional alloy. Zinc just takes the place of some of the copper atoms in the three-dimensional structure of copper. Substitutional alloys change characteristics of the metal like conductivity, reactivity, color, resistance to corrosion. So substitutional alloys change those types of characteristics. The other type of characteristic, and this is why those holes are important, is what we call an interstitial alloy. So an interstitial alloy relies on having much smaller atoms packed into the alloy, and these fit into the little spaces between the atoms. And when they do that, they make it so that it is harder for the various atoms of the metal to slip past one another. And so interstitial alloys, generally speaking, make metals much harder and more resistant to change. Okay, one more thing to talk about, and then we'll do practice problems. So last one, we'll come back to this when we talk about solids, but I wanted to talk about it while we're talking about bonding as well. And this is something called network covalent solids. And network covalent solids are a very unique application of covalent bonding. Instead of having 1 or 2 or even 5 or 6 or 12 covalent bonds between atoms, this is a we call it a macromolecule. So this is sheets, either 3-dimensional or 2-dimensional, hundreds of thousands of atoms all covalently bonded together. But like ionic compounds, it's not discrete molecules, okay? Network covalent solids are always formed from nonmetals. They usually contain at most 2 elements, okay? Frequently, they are the same element throughout, so carbon and silicon both form network covalent solids. This happens a lot with carbon because it's capable of making so many bonds. It can also happen with 2 nonmetals, so for example, silicon dioxide or silicon carbide. And then we have, again, just those 2 elements in this 3-dimensional structure. Okay, so let's go back and do a little bit of practice with ionic compounds. We're gonna quickly go over, we remember isoelectronic means the number of electrons is the exact same. So if we were to take neon as an example, oxygen, when it forms the oxide ion, is isoelectronic with neon, as is nitrogen and fluoride. All of those are isoelectronic with neon, as are sodium and magnesium. And we know that the cations are going to be the smallest, so magnesium is the smallest, followed by sodium, followed by neon, followed by fluoride, followed by oxide, followed by nitride. And this is important because as we start talking about Coulombs Law and applying that strength of attraction, it's important that you know the relative sizes of the ions. Okay, which compound has the most exothermic lattice energy? So if we look at the first pairing, sodium chloride and potassium chloride, the charges are the same. The only difference is in the radius, the size. And since the difference is between sodium and potassium, and we know that potassium is in a lower energy level, or higher energy level, lower period on the periodic table, we know that potassium is going to be larger, and so it's going to have a weaker Coulombic attraction, which means it has a less exothermic lattice energy, which means sodium chloride has a more exothermic lattice energy. Oh, whoops, let's talk about one other. Okay, so if we were to talk about the difference between magnesium hydroxide and magnesium oxide, we have a +2 here, a -1 here, +2 and -2 here. So charges are definitely in the favor of the magnesium oxide. And then the oxide ion is smaller than the hydroxide ion. And so magnesium oxide is going to have a much more exothermic lattice energy. And then when we compare iron 2 hydroxide and iron 3 hydroxide, the fact that we have more negative charges here and a more positive charge here, this is a +3, this is only a +2, tells us that the iron 3 hydroxide is going to have a more exothermic lattice energy. Okay, this one is kind of what we talked about with the formation of sodium chloride. The process, so the ionization of potassium is endothermic. The electron affinity of bromine is exothermic. Putting them together, the overall process is endothermic, but the overall formation of potassium bromide is exothermic because of that energy that is released from the electrostatic attraction of the potassium ion for the bromide ion. Okay, last one like this. So lattice energies of iron 3 chloride, iron 2 chloride, and iron 3 oxide. So we know that here we have a +3 iron, here we have a +2 iron, and here we have a +3 iron. So these two are both going to have stronger lattice energies, the iron 3 chloride and the iron 3 oxide. Then when we come to charge, the charge on the oxide ion is stronger, higher than the charge on the chloride ion. And so iron 3 oxide is going to have the highest lattice energy, most exothermic lattice energy. So that's going to be the 14,774. And the iron 3 chloride is going to have a higher lattice energy than iron 2 chloride. So that's going to be the 5,359. Okay, particle diagrams. College Board loves particle diagrams. So which one of these represents an ionic solid? Well, this one kind of has alternating, but they're in clumps, and we're never going to see two negative ions next to each other and then two positive ions next to each other. So that one's out. This one has alternating positive and negative charges, so that looks like that's probably our best choice. This has all of the negative charges next to each other and all the positive charges next to each other. That's not going to work because these positive charges would repel each other, as would the negative charges. And this isn't a solid at all. It's representing a gas. So how would it differ if they weren't in a 1-to-1 ratio? Well, if we had a -2 ion and +1 ions, we would see more +1 ions surrounding each -2 ion. Okay, let's jump to practice with metals. There we go. Okay. Copper atoms and zinc atoms have nearly the same atomic radius. So which one of these would represent an alloy containing only copper and zinc atoms? Well, we know they're atoms, so we can rule out this one with the positive and negative charges. That's representing an ionic compound. These are all the same, so that's not going to work. And this one, we have an interstitial alloy, not a substitutional alloy, because these are smaller and they're fitting into those holes, those interstices. So B is going to be our alloy that contains copper and zinc that are about the same size. And then one last practice question. So we have this sea of electrons and the cores or the nuclei. Metals are malleable and ductile, and that is because the electrons are totally equally shared and form non-directional bonds, so that when we hit this with a hammer, make it malleable, everything spreads out, both positive and negative, and nothing is impacted. So that finishes up the discussion of ionic bonds and metallic bonds. And as always, let me know if you have any questions.